Welcome back, class. Today we are going to start talking about some bonding theories beyond Lewis theory. So as we've talked about, Lewis theory is a generally simple bonding model. Now, simple doesn't mean inaccurate or bad. Lewis structure does a great job of making what we might call first approximations or first, guesses, if you will, or first level information about molecules. And it does a fantastic job of giving us general information, general shapes, skeletal structures. You combine it with VSEPR and we get a good idea of geometry for most molecules, but it can't give us as accurate, or it can't give us very good numerical ideas. And so some of the issues that Lewis structure has, I've written out here. It doesn't give good bond lengths or bond strengths, and in general doesn't give good numbers, right? It gives us a qualitative idea of the structure, while it also gives us good qualitative geometries and shapes. When we use VSEPR, it doesn't give us the actual bond angles of individual molecules for most things. It also has one of the limitations that we've talked about is the idea of resonance, right? It can't give us that one hybrid structure. It can only give us the resonance structures that contribute potentially to that hybrid structure. So that's, a nice big limitation there. It also can't predict, some key properties like magnetic behavior. Remember we talked about that in the previous chapter, paramagnetic versus diamagnetic. Doesn't do a very good job of predicting that in all molecules. O2 is a big example, right? We know it's paramagnetic, even though Lewis structure tells us it should be diamagnetic. So for all of these reasons, we're going to explore some more advanced bonding theories. And these more advanced theories will move into using quantum mechanics. So we spent an entire chapter developing quantum mechanical orbitals, right? Or S or P or D or F orbitals, right? But notice Lewis theory doesn't really ever use those. We just use the valence electrons. We sort of think about it, and we might in the back of our mind say, okay, this is, when this bond occurs, right, the orbitals are overlapping, etc., etc. But it doesn't really utilize any of the ideas of quantum mechanics. These bonding models that we're going to talk about in the next few lectures will use quantum mechanics. They're quantum mechanically based. So the first one we're going to talk about is something called valence bond theory. And valence bond theory is really an extension of quantum mechanical model. And we utilize the quantum mechanical orbitals when we think about this theory, or when we apply this theory to molecules. And so if we think about some of the basic points that we think about in bonding. So the idea when we use quantum mechanical orbitals is when a bond forms, right, orbitals are interacting, right? And so we want to have those orbitals overlapping in space, and when those orbitals overlap, those electrons pair up to make a bond, right? And so what we think about is each orbital supplying one electron, and those two orbitals coming together, and we end up with an orbital overlap with two electrons, right? Just, these covalent bonds, as we've talked about, are two electron bonds, and we get that bond, right? That orbital overlap with two electrons. Now, we'll see as we walk through, sometimes when we do this, in fact, most of the time, we have to utilize something called hybridized atomic orbitals. So right now, I want to make a key point, and this is just a vocabulary thing, and so you need to get used to this language. So when we talk about the S, the P, the D, the F orbitals, right, we're going to call these standard atomic orbitals. Okay. So standard atomic orbitals, these are the S, the P, the D, the F. So standard Those are the basic ones. Atomic means they're atom-centered, right? They're located on an individual atom. And of course, they're orbitals. Now, sometimes when we apply valence bond theory, we need to do something called hybridizing atomic orbitals. And we'll talk more about that as we go through here. But hybridized atomic orbitals are a type of blend or combination of the orbitals, where the orbitals take different forms, different shapes, if you will, based on the type of bonding that's occurring or the bonding environment, the electron environment. And again, I will mention this several times, but when we start thinking about these ideas, it's important to remember that these orbitals are just manifestations of mathematical formulas, right? These are not like objects that we actually have to change, right? It's a mathematical change, right? It's a mathematical model that captures where the electrons are going to most likely be, right? It's a probability map. And so if that probability changes based on the environment, then it makes sense that the orbital would change as well, right? Because that's what that's what the mathematic function is doing. Okay. And so we'll get more into that. But we want to be able to, when we talk about things and I refer to things in questions, when I mention standard orbitals, I'm referring to the s, p, d, and f. When I mention hybridized atomic orbitals, I'm referring to those hybridized orbitals, and we'll talk about the names and different types of those as we go through here. Okay, so for a bond to form, the key thing that we think about is lowering of energy, right? The reasons bond forms is stability, right? We don't form bonds that are going to raise the energy, that are going to make something more unstable, right? Bond forms, number of bonds form, the bonding environment is is such, the geometry is such, all in order to minimize the energy. And so, as I think I mentioned, just to reiterate, we visualize a bond with the overlap of two half-filled orbitals, meaning one electron, and those two electrons do what we call spin pairing when they bond, right? Meaning one is spin up, one is spin down. Now, we do see examples where both of the electrons come from one atom and they bond with an empty orbital on another atom, but that's less common. Now, we will make later this connection between geometry and the shape of these hybrid orbitals, or what orbitals are being used, whether they use standard orbitals or hybrid orbitals, is intricately linked or to the geometry or the shape of the molecule. And remember, the shape is linked to the electron distribution around that central atom. Okay, so let's get a little bit more into this and think about it. And something I want you to think about as we go through this is that as we form these molecules, remember, the areas where we find electrons will change, right? As bonds form, electrons are going to be at those locations where the most stable bonding environment can form. So electrons are going to change the areas that they reside in to lower the energy, maximize the orbital overlap to give stable bonds. Okay? So let's just start by thinking about a bond forming. And we have a diagram here of hydrogen. And the idea is that two atoms approach each other, right? So we think about here, right? They're far apart, right? We have just the energy that would be related to the two individual atoms. As the atoms move closer to one another, right, that energy starts to lower, right? We see a lowering of the energy as we get those attractions and so forth. And as they move closer, they lower the energy, and at some point we find a minimum. And that minimum energy is going to be where the bond length occurs. So the idea is that these two atoms are going to come together and they're going to get as close as they can to minimize the energy. Notice if they try to get any closer, the energy goes back up. So those repulsions that we talked about start to come into play more, and we lower the stability. So when we form a bond, the atoms get as close together as they can to minimize the energy, and we get a stable bond. And so again, the reason these bonds form, right, is the energy of the bonded atoms here is lower than the energy of these separate atoms. And that's stability. So let's start with a simple example of H2S. So we have a sulfur atom. We envision a sulfur atom has its s orbital and 3p orbitals. And remember, it has 6 valence electrons. They're going to be distributed as we see here, right? 2 in the 3s. We're going to have a total of 4 electrons in the 3p. 2 of the orbitals are going to be half empty. 1 is going to be full. These are the orbitals that we envision, could contribute to bonding, right? We have half-filled orbitals. Now, as the hydrogen atoms approach, right, of course, hydrogen's orbitals are half-filled, right, because hydrogen has 1 electron, so its 1s orbital is half-filled. And so we visualize an orbital overlap of the 1s orbital of hydrogen with the half-filled 3p orbitals of sulfur, and we get something that might look like this here, right? And based on the geometry of these orbitals, right, the p orbitals are going to be at 90 degrees, right? We have our px, our py, and our pz. And so that means if we form these 2 bonds, right, then these hydrogens should be at a 90-degree bond angle. And this is a very nice prediction for H2S, right? H2S has an actual measured bond angle of 92 degrees. So this bonding model makes perfect sense here, right? We have p orbitals, half-filled p orbitals of sulfur overlapping with half-filled hydrogen orbitals to form a bond. So using standard atomic orbitals in a molecule like H2S is perfectly reasonable. Now, I'll also point out that we have one of the p orbitals, right, that was already filled. And just to remind you, right, the Lewis structure of H2S looks something like this, right? One of these 2 orbitals would be from our p, right? The other one is going to be in our s, right? So those are where the 2 lone pairs, the 2 sets of lone pairs are going to be. And then we have our bonds. Okay. So for H2S, right, simple valence bond theory using standard atomic orbitals works really well. And we don't really have to do anything in terms of what we call hybridization. But this is not the case in all molecules, right? As we get to molecules that bond more and more, right? This idea of using the standard orbitals to make bonds and that predicting our geometry doesn't work very well. And we'll do an example to show that. And so if we take carbon, for example, right? So carbon is 2s2, 2p1, or excuse me, 2p2. And we might visualize something like this, right? Where we have one electron in the px, one electron in the py, and the pz is empty. Now, if I were just to think about it this way, right? This would predict 2 bonds, right? Because we have 2 half-filled orbitals. We have a px and a py that are half-filled. And those orbitals bonds would be 90 degrees apart. But carbon, we know, really, really likes to bond 4 times, and often those bonds are in the shape of what we call the tetrahedron, right, which are 109.5 apart. So how does that measured geometry result from these standard atomic orbitals that are 90 degrees apart overlapping? And the fact is, it doesn't very well, right? So one of the things that we do to sort of how we change the theory, how we pose the theory to account for these, is the concept of hybridization. And so the idea that these atomic orbitals hybridized before bonding or during bonding, however you want to think about it. But the idea is, as these bonds form, the electron environment is changing, right? And so the electrons are going to arrange themselves so they can make the most stable bonds. And if this carbon atom wants to make 4 bonds, well, then the most stable electron arrangement is to have those bonds 109.5 degrees apart, or something very close to that, right? Not 90 degrees apart. So the shape of the orbitals change to accommodate this more stable bonding environment. And so when we visualize hybridization, we in essence mix or combine, mathematically speaking, right, the orbitals, right? So we no longer will have our standard atomic orbitals. We will mix or combine the orbitals in order to get these new probability areas, these new orbitals that represent the bonding environment. So let's look at one type of hybridization that would occur in this particular example. Okay, now let's first look at why we can't use standard orbitals. So let's take a picture of what I was just explaining on the last slide. So we have our hydrogen, right, with our 1s orbital, half filled. We have carbon, 4 electrons, 2s2, 2p2. So you can see we have 2 half-filled orbitals. These are nice and set up to make 2 bonds here with hydrogen, just like we saw in H2S. And we would expect these to be at 90-degree angles. But we know that this is not the compound that forms, right? When we simply bond, hydrogen forms compound with carbon, right? The common form is this, right? CH4, right? With 4 carbon atoms, 109.5 degrees apart. So there's no really way that we can rationalize how we get from this bonding idea to this structure, right? Without changing the orbitals somehow. Okay. So this is again where hybridization comes into play. So let's think about this idea of valence bond theory. Let's do a little catch up here, a little review. So the valence electrons of the atom molecule, again, reside in these quantum mechanical orbitals. The orbitals can be standard PD, SPD, and F orbitals, like we saw in H2S, or they may be hybrid combinations of these, or hybrid orbitals. So Remember, the bonds that we're thinking about are when atomic orbitals interact and there's a total of 2 electrons in the new bonding orbital. And these electrons are spin paired. So not only do we typically make a certain number of bonds like we saw, but we need the orbitals to only have 1 electron in them, not be paired, right, if we're going to make that many bonds. And so we need to have a new type of orbital or a new shape of orbital to accommodate that. And again, there is an intimate connection between the shape of the molecule, right, again, which is governed by the distribution of electrons, and the geometry of the orbitals, right? They have to match, right? The geometry of these interacting orbitals must match up with the observed shape of the molecule, right? That's the only way that we can get agreement between theory and measurement, right? When we measure the geometry, we can actually get the real geometry doing X-ray crystals and so forth. That geometry has to match up with what the theory predicts. Otherwise, the theory is not doing its job correctly. So what's happening when we hybridize? So now, again, this isn't always the case. So things like H2S don't have to hybridize, right? And not every orbital has to hybridize. For example, when we look at these, we'll see that the hydrogen orbitals don't hybridize. Only the ones on the carbon hybridize. So not every orbital hybridizes, but some orbitals, some atoms, their orbitals hybridize when we create that bonding environment. Typically, it's the central atom that hybridizes. Hybridization is more likely to occur when we have more bonding, right? So if there's more bonding, there's more need to alter the electron shape around the central atom to account for those bonds to get the lowest energy bonding possible. Hybridization can occur in different ways, right? Different orbitals or different combinations of orbitals can mix or combine to give you these, quote, hybrid atomic orbitals. And here are the 5 types that we're going to look at. Now, just a quick look at the names here, and I'll go over this again, but the names come from the orbitals that are combining, right? It's really, once you see it, it's not really hard. But for example, the first one we're going to look at is sp3, and this is a combination of an s orbital and 3 of the p orbitals, so all 3 p orbitals. So s, p3, the 3 here means that we're using all 3 of the p orbitals, and we're combining that with an s, so we have 4 standard atomic orbitals that we're combining and hybridizing to make the hybrid orbitals. Now, an atom doesn't always do the same type of hybridization. Again, it's going to depend on the environment, the bonding environment. So carbon can do many types of hybridization depending on how it's bonding. One thing to always keep in mind is that the number of standard atomic orbitals that we put together, so in sp3 we're putting 4, we're always going to get the same number of hybrid orbitals out of that. So if I combine 4 standard orbitals, I'm going to get 4 hybrid orbitals, right? So we don't have fewer orbitals, they're going to be different shapes. Hydrogen doesn't hybridize, right? It's always the terminal atom, right? It doesn't have the orbitals, right? It only has 1 orbital. So don't ever try to hybridize hydrogen. The number and the type of standard orbitals that come together determines what the hybrid orbital looks like. So it determines the shape and also the energy of the hybrid orbitals, right? So again, we're going to form hybrid orbitals that are going to minimize the bonding energy or the energy of the bonding environment, right? To make the molecule stable as possible. Okay? So we're going to yield the lowest overall energy for the molecule. Okay. So these are some of the basics as we contemplate hybridization. So we're going to wrap up this lecture, by looking at one type of hybridization. and that's probably the most common or the one that we see the most, and that's sp3 hybridization. Now, sp3 hybridization is linked to a tetrahedral geometry, or where we have 4 bonds around our central atom. Right? And so, in order to accommodate that, we need to have 4 orbitals, right? And as we've already discussed, right, with methane, right, using standard orbitals doesn't give us the right bonding geometry to create what we actually see, a tetrahedron. So if we visualize hybridization, we take our set of 4 hybrid orbitals, sp3, right? We hybridize them. They combine, change shapes, whatever you want to think about it, right? So as these bonds are forming, the electrons will move or orient themselves in order to give the minimal energy bonding environment. And as we've discussed, that minimal energy bonding environment when we're trying to make 4 bonds is to have those bonds approximately 109.5 degrees apart. And so we go through this hybridization occurs, and we get 4 new hybrid orbitals. And notice these orbitals a little bit. First of all, they're pointed 109.5 degrees apart, right? At the corners of our tetrahedron. Notice their shape, right? First of all, they're all identical, but look at the lobes, right? The electron density, or the probability of finding the electron, is directed where the bond is at, right? So the bond is going to occur here, right? So the electron is much more likely to be found here than it is on the other side. So like a p orbital, right, the lobes are not the same size. And if we, just sort of to vision, we put all of these on top of each other, we get something that looks like this, which looks like our tetrahedron. And so this is another way to visualize it here. We start out with our 2s2, 2p2. We form our hybrid orbitals. Now, anytime we form hybrid orbitals, I don't know if I mentioned this, they're always of equal energy, right? So the book will use the term degenerate energy, right? It just means they're all the same. And so when we put these 4 valence electrons of carbon into these hybrid orbitals, notice we end up with 4 unpaired electrons in those 4 orbitals, right? Following Hund's rule, where we put them in one at a time before we pair. And again, this is going to give us the perfect setup to make 4 bonds, like we would see in methane. So now we have 4 hydrogens bringing their 1s orbital with their 1 electron, combining with the 4 sp3 hybrid orbitals, which are displayed in the form of a tetrahedron, to give what we visualize as the shape of methane. And again, this corresponds very well to what actually the shape of methane is and what the bond angles are, etc. So we can see here how hybridization much more accurately allows us to explain what really happens in the bonding. Now, carbon is not the only one that we can do this. Another quick example where we see sp3 is in ammonia. So remember, nitrogen, right, unlike carbon, has 5 electrons. And so it's going to have another electron here. So if I do this for nitrogen, for example, it's going to have another electron here. And so when I go to fill this up, one of these is going to be filled. This filled one is going to end up with the lone pair that we see on ammonia. So remember the Lewis structure of ammonia is like that, where we have a lone pair on the nitrogen, and it takes up a trigonal pyramidal geometry, right? 4 electron groups still. So the electron groups are still approximately 109.5 apart, but we have the lone pair there. and that's going to be represented by one of the sp3 orbitals already being filled, right? And so there's 3 left to make bonds. So this sp3 hybridization is what we often invoke anytime we have a bonding environment where we have 4 electron groups. Okay, so I'm going to end this class here, and next time, in the next video, we will talk about some other forms of hybridization that occur.